The desert does not look alive at first. At noon, it appears emptied by heat, scraped clean by wind, reduced to light and mineral and silence. But the stillness is deceptive. Just above the surface, the air trembles. A few centimeters below it, the temperature begins to change again. Sand that burns by day can cool with startling speed after sunset. And between those two extremes, an entire hidden biology waits, measuring every second. Here, movement itself becomes a problem. Breathing becomes a cost. Touching the ground too long can be dangerous. And in the most punishing places of all, the animals that remain do not simply endure the desert. They become shaped by it in ways that look almost unreal. Today we're diving into why desert snakes get stranger the hotter you go. Why, in the fiercest landscapes on Earth, ordinary serpents seem to give way to sidewinders, sand swimmers, buried ambush hunters, and heat-sensing predators that navigate a world our own senses barely perceive. Heat is not just one pressure among many in the desert. It is the force that reorganizes everything. For a snake whose body temperature depends heavily on the outside world, a hot desert is not simply dry terrain with little shade. It is a place where the window for safe activity narrows, sometimes to the edges of dawn, dusk, and night. In Death Valley and other North American deserts, the sidewinder rattlesnake shifts toward crepuscular and nocturnal life during warmer periods, disappearing into burrows or into the sand itself through a behavior known as cratering. What looks like absence is often timing. The snake is still there, but the hours in which it can hunt, travel, and reproduce have been squeezed by temperature into smaller and stranger slices of the day. The hotter the habitat, the less useful ordinary reptile routines become. Surface exposure, long straight crawling, and open daytime movement begin to fail. Under those conditions, weirdness is not decoration. Weirdness is engineering. That is why the story of desert snakes is not really about venom first, or even fear. It is about constraint. Loose sand collapses under force. Bare ground radiates heat back into the body. Water is hard to replace, and every unnecessary movement increases both thermal risk and dehydration. Recent work on Sonoran desert rattlesnakes shows that rainfall patterns influence both behavior and physiology, including activity and evaporative water loss. In other words, aridity does not merely make life harder in a vague sense. It reshapes the balance between motion, water, and survival at the level of the body itself. Some species can rely heavily on water obtained from prey, rather than from standing sources. Others spend long hours secluded, reducing exposure instead of trying to outcompete the desert directly. The result is a world in which selection favors precision over power. Move less, move smarter, and if possible, let the environment do part of the work for you. Nowhere is that precision more visible than in the strange diagonal calligraphy that some snakes leave on dunes. The sidewinder rattlesnake of the American Southwest does not cross sand the way most snakes cross soil or rock. Instead of keeping much of the belly in contact with the ground, it lifts sections of the body and throws them sideways in a looping sequence, so that only a few points touch the surface at any moment. The movement looks uncanny because it solves several problems at once. It reduces contact with hot sand. It prevents the animal from pushing too hard on a substrate that easily gives way. It allows surprisingly rapid travel across terrain that defeats many limbless machines. When researchers tested sidewinders on sandy slopes, They found that as the incline increased, the snakes increased the length of body in contact with the sand, spreading force so the dune did not collapse beneath them. It is not just sideways movement. It is active negotiation with a material that is half solid, half avalanche. And this is where desert snakes begin to look stranger the hotter and sandier the world becomes. Evolution starts arriving at similar answers in different places. In North Africa, the Saharan horned viper and the Saharan sand viper also sidewind across dunes, even though they are not close copies of the American rattlesnake. One study comparing their skin found something even more revealing. Many snakes that move by ordinary forward undulation have microscopic head-to-tail spikes on their belly scales that help generate directional friction. But in sidewinding species, researchers found belly surfaces dominated by tiny pits and far fewer or no such spikes textures, better suited to a style of locomotion that needs low directional bias and minimal drag. The deserts themselves may even help explain degrees of specialization. The Sahara's sandy conditions are vastly older than the young sand seas of the Mojave, and researchers have suggested that this difference in time could help explain why African sidewinders appear more fully specialized in certain skin features. The habitat is not just selecting behavior, it is reaching down into the microstructure of skin. But crossing the surface is only one solution. In the hottest deserts, many snakes choose to stop being surface animals at all. The Saharan horned viper, Cerastes cerastes, is often found buried or half-buried in soft sand, with only the eyes and nostrils exposed. By day it may vanish into burrows, holes made by other animals, or shallow cover beneath shrubs and debris. In this posture it is doing two things at once, escaping the worst heat and turning invisibility into a hunting tactic. The desert here is not an empty stage but a layered medium, with safer temperatures just below the skin of the dunes. The sidewinder rattlesnake uses a similar tactic in North America, sinking almost completely under the surface while it waits. A line of tracks ending in a small depression can be the only sign that anything is there. The body disappears, the strike remains. In this world, one of the most successful forms of adaptation is learning how not to be seen, even by the sun. The horned vipers of North Africa add another layer to that illusion. Their broad, flattened bodies blend into yellow-grey sand so effectively that outline begins to dissolve. Their horn-like scales above the eyes are among the most iconic features in any desert snake. Though their precise function has been debated, they are thought to help in sandy environments, possibly by protecting the eyes or disrupting the shape of the head. More certain is the lifestyle that surrounds those ornaments. These vipers are ambush predators. Buried in place, they detect prey through vibration, vision, and in pit-bearing species, thermal cues, then erupt from concealment with explosive speed. Even the posture of hiding reveals an evolutionary logic. In deserts, pursuit is expensive. Chase requires long exposure, more energy, more contact with hot ground, and more risk of being seen. Waiting is often better. The harsher the surface becomes, the more natural selection rewards snakes that can turn stillness into a weapon. Some species go further still, leaving the surface almost entirely, and moving through sand as if it were water. The shovel-nosed snake of the Mojave Desert is one of the most elegant examples. Researchers using X-ray imaging found that this long, slender snake propagates waves down its body beneath the surface, traveling mostly within the same tunnel of disturbed sand created by its wedge-shaped head and body. Its form matters enormously. Compared with the stockier sandfish lizard, the snake's high length-to-width ratio allows it to generate more effective body waves, move faster, and do so more efficiently. Its skin also appears to reduce friction, lowering the energy cost of burrowing through a granular medium that resists and shifts at the same time. This is not simply a snake hiding underground. It is a body reconfigured for a second desert landscape, one just beneath the visible one, where sand becomes a temporary fluid and locomotion demands a different kind of physics. Seen together, sidewinding and sand swimming tell us something profound about why hotter deserts produce stranger snakes. Extreme environments do not merely push species to their limits, they sort among possible body plans. On hard ground, a generalized snake can do many things reasonably well. On burning dunes, generality begins to break apart. A long body becomes a way to distribute force. A low-friction skin becomes a way to save energy. A wedge-shaped snout becomes a tool for entering a collapsing medium. Specialized movement is written not only in behavior, but in shape, texture, and proportion. The desert is a biomechanical filter, and over evolutionary time it removes what is inefficient with ruthless consistency. What remains can look bizarre to us only because we are seeing an animal that has been redesigned by a landscape with almost no tolerance for compromise. Then night falls, and another transformation begins. Many desert snakes do not just avoid the sun, they inherit the dark. In those hours, when the thermal structure of the landscape changes and prey begins to move, some vipers bring online a sensory system so unusual it once seemed almost mythical. Pit vipers possess heat-sensing organs between the eye and nostril on each side of the head. These pits do not see infrared the way a camera sees it. They register thermal contrast. Warm animals moving against a cooler background become detectable even in darkness, allowing a coiled rattlesnake to aim into the night at a mouse-sized source of heat. For an ambush predator in a place where daytime movement can be costly, this is a remarkable adaptation. It shifts the hunt into safer hours and lets the snake exploit prey that is active when visual information is poor. The desert at night is not blind. It is mapped in gradients of temperature. At the molecular level, that ability is stranger still. Research has shown that pit vipers use TRPA1 ion channels in the sensory nerves of the pit organ to detect radiant heat. In most vertebrates, TRPA1 is better known as a receptor involved in chemical irritation. In pit-bearing snakes, evolution has repurposed it into an exquisitely sensitive heat detector. The pit membrane acts as a passive antenna for thermal radiation, and minute changes in temperature trigger nerve signals that help locate prey. Yet even this famous sense is not magic. Studies of pit viper thermography suggest the system has poor spatial resolution compared with modern thermal cameras. It works best when prey stands out from the background in strong contrast. That limitation makes sense. In the real desert, a snake does not need a beautiful image. It needs a usable one. Enough information to orient, strike, and survive. Evolution has not built a perfect instrument. It has built a sufficient one, tuned to the margins between warm body and cooling sand. Water, meanwhile, remains the quiet ruler behind all of this. Desert snakes live in places where the cost of losing moisture can be as serious as the cost of overheating. For species like the Saharan horned viper, prey may provide the only meaningful source of water. That helps explain the advantage of ambush hunting, long inactivity, and deep association with sheltering substrates. It also helps explain why activity patterns track rainfall so closely in arid rattlesnakes. When precipitation shifts, behavior shifts with it. The classic image of a desert snake as a simple, cold-blooded survivor misses the deeper truth. These animals are managers of budgets, heat budgets, water budgets, risk budgets. Every bizarre trait that catches the human eye, from diagonal movement to partial burial to heat-sensitive pits, is part of a larger accounting system in which waste can be fatal. The hotter and drier the habitat becomes, the more visible those calculations become in anatomy and behavior. So why do desert snakes get stranger the hotter you go? Because extreme heat narrows the number of workable solutions. It forces evolution away from the ordinary middle and toward specialized edges. Some species learn to touch the ground less. Some learn to vanish into it. Some move through it. Some turn darkness into a field of thermal contrast. Again and again in distant deserts and separate lineages, similar pressures produce similar inventions. Sidewinding in North America and North Africa, reduced drag on sand specialist bodies, buried ambush tactics where motion is costly, sensory systems that let hunting continue when the surface cools. These are not curiosities scattered at random across the reptile world. They are repeated answers to a brutal question asked by hot sand. How do you remain an active predator in a place that seems built to shut activity down? And still, the desert keeps part of the story to itself. We can measure friction on scales, image bodies moving beneath sand, map infrared pathways in nerves, and model how a dune fails under the pressure of a moving snake. But there is a limit to what those measurements capture. We still do not fully know how many small advantages combine to make one lineage endure while another disappears. We still cannot watch most of these animals live out their lives in the hidden hours beneath the sand. We know enough to see the pattern. The harsher the desert, the less a snake can afford to remain ordinary. Yet the full conversation between heat, time, and evolution is still unfolding under dunes, in burrows, in the brief, cool hours before dawn. The strangeness of desert snakes is not evidence that life has escaped the rules. It is evidence that life has obeyed them so completely, and for so long, that the result now looks almost impossible.